So we've talked about the theory of operation of FETs. Let's talk about how we can use them in circuits. And how we can do that is in pretty much the same manner as we would use a BJT transistor. So here I've got an example of a BJT amplifier in a common emitter configuration. And what I've done is I've biased this transistor by adjusting the values of R1 and R3, the base resistors, in order to get the output of the collector at about halfway in the middle of the load line. And what I'm doing is I'm trying to adjust these two parts so that I can get a good swing in both directions from the default center point. Let me show you how that's done in an example here. So here's the same circuit I just showed you, a BJT amplifier, and we've biased this one that the output is in the center of the load line by setting this to 7K. Now what I've done is I've taken that same circuit, but I've adjusted this lower base resistor here so that this voltage sits a little bit higher. And when it's a little bit higher, the collector will sit a little bit lower. And what will happen with this one here is that as the input signal comes in, this one will swing down and it'll hit the saturation point. And so what we'll see on this one here is we'll see some clipping on the bottom. So if you bias the base a little bit too high, you get clipping on the bottom. And then this one over here, what I've done is I've taken that 7K and I've reduced it. That drops the base voltage. The collector sits at a little bit higher point normally. And when we start putting in a signal, then this one will clip at the top of the sine wave. So let's start the simulation and see if that's true. So here I've got a scope. This is the center one here. This is the one that I've adjusted for the center of the load line. And you can see you've got a good sine wave with a good top shape and a good shape on the bottom. So now let's pop this one open. This is the one that I've biased the base voltage a little bit too high. And so what you're seeing with it is I'm getting clipping at the bottom. And then this one over here, I have biased it a little bit too low on the base voltage, so the collector sits a little bit too high. I'm getting some clipping at the top. So this is kind of like Goldilocks and the Three Bears, where this one is biased too low, this one is biased too high, and this one is just right, and I get a good swing in both directions from the center point. So here you can see that I've applied the same input voltage to the BJT amplifier and the FET amplifier. And over here on the scope, I've got Vout1 and Vout2, and I've got them overlaid on top of each other. If I move this down, you can see that there is actually two waveforms there. So let's go ahead and start the simulation. So here you can see that with a 0.1 volt peak input, the two outputs are pretty much one on top of the other. There's a little bit of a gap down here, but I would say that the gain characteristics of these two amplifiers is almost identical. But if I start to increase the voltage, so let's go from 0.1 to 0.2 volts on a peak input. So let's double the input swing and then readjust to get it the same shape, the same size on the oscilloscope. So now you can see that this has gotten a little bit bigger here, the difference between them. This is because the FET's not as linear as a BJT. So as we increase the input voltage, the gain does change slightly. And then if I go to 0.4 now, if I double it again and increase to 2 volts per division, you can see that every time I increase it, the gap here gets a little bit bigger. So the conclusion is that we can use the N-channel enhancement mode FET in the same manner as we use a 3904 NPN transistor. And the same is also for P-type. If I have a PNP transistor, I can replace that with a P-channel enhancement mode FET. They're very similar in the operation. The gain characteristics on a large signal will not be quite as linear. Now you can get rid of this difference if you use an operational amplifier with feedback, and you're going to learn about that in your next course. But so far as the non-feedback amplifiers, the FET amplifier has characteristics that are very similar to a BJT amplifier once you've adjusted for the slight differences in the part that this is a voltage to current and this is current to current. So you got to bias them a little bit different and you got to play with these resistor values to get the same gain, but then they do pretty much the same job. The TIP 120 comes in a TO220 package, which looks something like this. And the FET that I'm going to compare it against comes in an SO8 package, and it comes in a package that looks like this. Although this isn't life size, these are both to the same scale. So you can see that the FET that I'm going to compare this transistor to is a heck of a lot smaller. So let's go ahead and turn on the transistor and start the simulation. So here we are, we're running the simulation, and right now I've got the input to the transistor is low, so the transistor is in the off state, and I've got about 12 nanoamps going through the transistor, and it's got about 12 volts across it. So this transistor is off, and there's virtually no current going through the load. It's in the nanoamps. Now I'm going to go ahead and apply a high voltage to the base of the transistor. It turns on, pull this point low. I end up with 5.39 amps going through the transistor and about 1.22 volts across it. So although it's in saturation and we're using it as a switch, it's not a perfect switch. It still has a voltage drop across it when it's got a current through it, and that means it's going to be dissipating power. Let's calculate how much power it dissipates. So it's got 5.39 amps through it and 1.22 volts across it. That means that the TIP 120 is dissipating about 6.5 watts of energy. The load resistor has the same current through it, but it has 10.78 volts across it, so it's dissipating 58 watts. So we can figure out the efficiency. We deliver 58 watts to the load, putting in a total of 65 watts. So the efficiency of this circuit is about 90%, which sounds pretty good. But if this guy is doing about 6 watts, it's going to need a heat sink and possibly a fan in order to keep the temperatures down and to stop it from blowing itself up. Let's compare that to the FET, which is in this SO8 package. So I found an IRF 7413 in the components database, and I plunked that down. And when I have it in the off state, I see there's 588 nanoamps through it, which is very little current, and it has 12 volts across it. Let's go ahead and apply a high voltage to this FET. Turning it on, it drags this point down to ground. So the bottom of the 2 ohm load is grounded and the top is connected to 12 volts. I now have 5.97 amps going through it and 58 millivolts across it. Let's calculate the power. So we said we have about 6 amps going through the FET and 58 millivolts across it. So that FET is dissipating 346 milliwatts. The load resistor has 11 volts across it, and it's doing 71 watts. So the efficiency of the FET circuit is about 99.5%. And if you look at how much watts is dissipated by the FET and compare that to the TIP 120, that looks like that's about 20 times the power dissipation in the FET. So that is a way better switch than that transistor. And this is the beauty of FETs, is that when they turn on, they become a very low resistance and they will dissipate almost zero power. So you can use them to switch very big loads. So what things should I look at in the datasheet if I want to choose a FET for a switching application? So the first thing that you want to look at is this one right here, usually at the top of the datasheet, called RDS on. And this is the resistance from the drain to the source when the FET is on. What happens with a FET is that when you turn it on, it starts to act like a resistor. And this can be a resistor with a very low impedance. So this particular FET, when I turn it on, it acts like a 0.011 ohm resistor. So if I put a current of 1 amp through that resistor, then the power that it dissipates, which is going to be I squared R, is going to be 1 squared times 0.011. That would be 11 milliwatts of power dissipated, which is a very low amount of power for switching a 1 amp load. You can get some FETs that are even lower than this. You can get FETs that have an impedance of 1 milliohm or even less than that. So they can conduct huge amounts of current without heating up. So the next characteristic on the datasheet that's important is this thing called VGS threshold. And that can be found right here on the datasheet, gate threshold voltage. And with this particular FET, the gate threshold voltage is someplace between 1 and 3 volts. So what that means is that when you approach about 3 volts, so this is VGS, when you hit 3 volts, that's where you're past the parabolic curve and you're going relatively linear on the slope of the curve here. So you're approaching the minimum on your on-state resistance. Now, what would be the on-state resistance at that point? You're not going to get the 11 milliohms. Just above that, you can see an example here that shows you what kind of static drain to source resistance you're going to get. So if you have a gate threshold voltage of 4.5 volts, you should be getting 18 milliohms of on-state resistance. That's not quite 11. How do I get 11? Well, if I put on a VGS, if I put 10 volts on the gate, then I should be achieving my 11 milliohms of on-state resistance.